All right, then welcome everybody to the last talk for this session by Henry about structural thresholds in doubly random temporal graphs. Please go ahead.
Okay, cool. So I'd like to start by thanking the organizers for giving me the dubious honor of talking last. And just as a logistical note, I had to make a last-minute dash into the office because my home internet failed. So if you see kind of ghostly shapes moving behind me, that's just my colleagues. The work I'm going to be talking about today is structural thresholds in doubly random temporal graphs, and this is based on joint work with George and Paul. So at this point in the day, I probably don't need to introduce what a temporal graph is, but for completeness, we consider a temporal graph to be a footprint graph with a set of edge labels which determine when those edges actually exist. Somewhat strangely, for this talk, these edge labels are going to be real numbers. This is because we need this for technical reasons to do with uniform sampling. But our results here are kind of purely structural, and if you need them to be finitely representable, you can get away with an arbitrarily good discrete approximation, so don't worry too much. Maybe slightly more exotic than a temporal graph here is a random temporal graph. And typically when we're talking about random temporal graphs, we really mean distributions of random temporal graphs that have some kind of property that we're interested in. And popular examples of this might be something like edge Markovian temporal graphs, random simple temporal graphs, or the random spanning tree model. And I think that random temporal graphs are a kind of really interesting alternate way to look at temporal graphs at the moment, both because random temporal graphs allow us to kind of look at the properties of the average temporal graph rather than just the edge cases that we're normally concerned with. And additionally, because I think an overwhelming theme in the temporal graph literature is that temporal graphs are incredibly expressive as a language. And random temporal graphs are another way of kind of tying our hands behind our back to go with like fixed parameter tractability or restricting the footprint. And so they can be a kind of useful and very difficult tool to work with. We're not going to be working with any of these kind of three big existing models. We're going to be working with a slight generalization of the random simple temporal graphs, which we call the doubly random temporal graphs, which I will now introduce. So doubly random temporal graphs, or the DRTG, as I will call it throughout, are a family of distributions of temporal graphs parameterized by a label distribution. And the label distribution controls how many labels are going to be on each edge. You can think of it as similar to the density parameter of an Erdős-Rényi random graph, if that's something you're familiar with. And the label distribution can be any arbitrary discrete distribution, pick your favorite, so long as it is supported only on the non-negative integers and has a finite non-zero second moment, which is true of most kind of reasonable discrete distributions. Once we have our label distribution, we can then obtain a sample from the DRTG corresponding to it by first sampling the number of labels on each edge independently and identically at random from this label distribution, and then for each actual label sampling its occurrence time uniformly at random. And this is where the name doubly random comes from, is because there's these kind of two sources of randomness. We have the randomness of the number of labels on each edge, as well as the randomness of when those labels actually occur. Some people in the audience may have kind of raised an eyebrow when I said uniformly at random, without actually specifying what I'm sampling from uniformly at random. And depending on what you choose, you can come up with a kind of plethora of related but different models. So the two that are maybe of relevance here are if we choose to sample uniformly at random from the interval 0, 1, we obtain something that we call the continuous DRTG. And if you choose to sample instead from a fixed set of integer snapshots, you get something which we'd call the discrete DRTG. The continuous DRTG is much more mathematically tractable to manipulate. And gives you much cleaner theorem statements. So it's what I'm going to be working with today. But in general, most of these results can be kind of moved over to the discrete version by using the relationship between the two. So hopefully that makes sense and everyone has a clear idea of what the DRTG is. You can think of it as just a kind of slightly more complicated Erdős-Rényi graph, if that is useful to you. But that's only half the title. The other half of the title is structural thresholds. And what do I mean by structural thresholds? Well, in particular, I mean examples where a very small change in model parameters leads to a very large change in some property of the random temporal graph. And this is something that shows up throughout all sorts of combinatorial structures, in particular random combinatorial structures, and even in random temporal graphs, we've seen a whole bunch of very nice like structural thresholds that show up in the random simple temporal graph as of late. But we're going to particularly zoom in on temporal motifs as a local property, which shows a structural threshold, and doubling times, which show as a global property with a structural threshold. Some of you may have heard of a temporal motif. In fact, they've already been introduced in disguise once in the talks today already. But temporal motifs are an alternative to temporal subgraphs that kind of come from the temporal network science literature. And temporal motifs look to solve the kind of fragility problem of temporal subgraphs. So for completeness, we say that a temporal subgraph we say that H is a temporal subgraph of G if we can obtain H from G by deleting vertices and edge labels. And this is a very natural, I would even say canonical way to define a temporal notion of subgraphs, but it ends up being incredibly fragile to the specific timings of the edge labels. If you add 1 to all of the edge labels of a temporal graph, you can completely change its set of temporal subgraphs. And this leads to temporal subgraphs being kind of very inefficient for expressing certain properties that we would like to be able to express about temporal graphs, like whether or not they contain a temporal, like time-respecting path of a given length. This is very inefficient to do with temporal subgraphs due to this fragileness. Temporal motifs solve this by, rather than requiring a specific matching between edge labels, the timing of edge labels, they instead require only that the edge labels obey a given partial order. So more precisely, we say that a temporal motif is a static graph and a partial order over a set of edge labels on that static graph. And we say that temporal graph contains a motif if there exists a temporal subgraph which has the static graph as a footprint and edge labels of that footprint which saturate and obey the partial order. For example, temporal motifs are very powerful. They can capture all of the following with a single motif. For example, fixed length time-respecting paths, time-respecting cycles, repeated edges, subgraphs of the footprint graph. These are all things that have corresponding temporal motifs. And you can even use them like people use subgraphs and static graphs, and by forbidding them, you can capture kind of natural temporal graph families, like simplicity and properness are both captured by motifs. I have a set of examples. The first is a time-respecting path on 3 vertices. This is captured by a motif, which is a path on 3 vertices with an order over the edges such that one of the edges must come before the other edge. Another example that we've seen already today is the temporal triangle from Fabio's talk. But in general, we do not actually require that we have a total order over the edge labels. We could have a partial order. So here we have kind of 2 converging temporal paths. And the requirement is only that EFIJ is a time-respecting path and GHIJ is a time-respecting path, without any relationship necessarily between the label on the edge EF and the label on the edge GH. Hopefully, this gives everyone a good understanding of what I mean by temporal motifs, although the exact details are less important going forwards. We're actually going to be using a slight specialization of temporal motifs, which we call the delta temporal motifs, and this corresponds to the delta instances from Fabio's talk from earlier. And a delta temporal motif is simply a temporal motif where we additionally require that all of the labels in the instance fall within a window of length delta. So, for example, in this case, we would say that a temporal graph contains this as a temporal motif if it has a temporal subgraph with this as its footprint, edge labels saturating and obeying the corresponding partial order, and where all of the labels occur within a window of length delta. This feels like quite a kind of artificial and constructed definition, although I was surprised to see it come up in another talk earlier. However, it actually does show up in kind of network mining and real practical problems. And one of these problems is in fraud detection. A classic problem in fraud detection is that you are given a big network of financial transactions, which should really be modeled as a temporal graph, and you wish to identify fraudulent transactions. And a classic type of fraud is money laundering, and a textbook way to do money laundering, if such a textbook existed, would be to send the same money via a cyclic sequence of transactions through a series of intermediaries back to yourself. And we would like to be able to find these patterns within a big temporal network. Unfortunately, we can't just look for motifs with a cycle footprint and a time-respecting ordering, because the economy is kind of fundamentally circular. If it wasn't, a small number of people would end up with all of the money. And so we have to deal with the fact that we will naturally see cycle motifs with a time-respecting ordering showing up kind of legitimately in this data. And so we either need to look for too many of these things showing up, or these things showing up within too short a period of time. And what this corresponds to is finding temporal motifs on a cycle footprint with a time-respecting ordering and a very, very small delta such that they are still instances. How small that delta is precisely motivates one of the kind of main things that we want to show in this, which is what the existence thresholds in terms of the time window are for specific motifs. And this is something that we were able to do. So for any fixed, strict, and simple motif, and here by strict we mean that the partial order must be strict, and simple we mean that the motif has at most one label on each edge, we're able to show that for any valid label distribution, a sample from the corresponding DRTG contains this motif as a delta temporal motif with high probability, so long as delta is little omega of n to the negative some parameter of the motif, and with high probability does not contain the motif so long as delta is below this threshold asymptotically. And so we see this kind of really tight thresholding behavior where if you're below this threshold with high probability, and by that we mean asymptotically almost surely, you do not see this motif show up at all. And the moment you go above this threshold, we do expect to see it. This parameter that I've been hiding up to this point is something that we call sparsity, and it's really a parameter of the footprint of the motif. For a graph G, the sparsity of G is defined as the minimum over all subgraphs containing at least two edges of the number of vertices in that subgraph over the number of edges minus one in that subgraph. And this is quite general, but I also think that there are kind of two interesting things about this statement. So the first is that you may notice that the order of the subgraph, the order of the motif and the label distribution do not show up in the threshold itself. And this is really because we hold them constant as the graph grows. And because they are of constant size, they just get lost in the asymptotics. If you allow your motif to grow with the size of the network, for example, if you look for something like the largest clique with a given ordering showing up within a given window, you will immediately see the label distribution and the ordering raising their ugly heads in your threshold, and it all becomes a lot more complicated. The other thing which is kind of interesting about the structure of this statement is that some of you who are more familiar with the random graphs literature may think that you've seen something very similar before. And that is because you may have seen this classic result by Bolobash for the existence thresholds of subgraphs of the Erdős-Rényi random graph. And the statement of this turns out to be very, very similar, other than the parameter in the exponent is the minimal reciprocal density, which is the number of vertices over the number of edges in the densest subgraph of the subgraph we are looking for, rather than this sparsity property. And I think this is quite interesting because it kind of tells us that the behavior of our subgraph analog in temporal graphs behaves closely, but not exactly like the static graph variant. And it also made life a lot easier because we were able to kind of use ideas from the random graph literature, like the whole proof is done via a first and second moment method, rather than coming up with ideas from scratch. But we were still able to get something which behaves a little bit differently. There's some actually quite nice justification for why we should expect this similarity between these thresholds. And so I'm going to try and give a little bit of intuition for why we can expect this threshold to lie where it does. So if you take the 0, 1 interval and you find a specific subinterval of length delta, and you ask whether a given temporal motif shows up in this window of length delta, if we kind of squint a little bit and throw out the order, we can say that the probability of it showing up in this subinterval is roughly the same probability of its footprint showing up in an Erdős-Rényi random graph with density delta. And then repeating this argument for a slightly larger interval of length 1 plus epsilon delta, we can argue that we would expect the probability of the motif showing up is roughly similar to that of the footprint showing up in a Erdős-Rényi random graph of density 1 plus epsilon delta. And then what we can do is we can cover the entire interval from 0 to 1 with these subintervals of length 1 plus epsilon delta. And then if a delta temporal motif shows up in any of them, its footprint will show up in one of these 1 plus epsilon delta intervals. And since we only need order 1 over delta subintervals to cover the full interval, we can essentially loosely trace through the argument for the static graph case with an additional 1 over delta factor via a union bound. And this 1 over delta factor goes through to cancel some things, which gives us this additional -1 in the parameter down here. This approach doesn't work in general. You need to be a lot more careful with the other bound, and especially if you want anything to grow. But I think it's a really nice demonstration of why we should expect this result to be the case. But I've just spent a bunch of time arguing about why this result is similar to a previous result. You might be asking, Henry, why should I care about this new result that you're presenting? Does this actually mean anything different from the static graph version? And the answer here is yes. And I think there's a really cute example which takes us back to our fraud detection motivation from earlier. So in the Erdős-Rényi random graph, all cycles have the same asymptotic existence threshold. As you increase the density from 0, at some point in the limit, all of the cycles emerge simultaneously. However, for cycle motifs in the DRTG, as we increase the window from nothing, we actually see that all of the cycle motifs, all the cycle footprints with the corresponding motifs, show up at a different point. They all have their own unique existence threshold. And in particular, the small cycles appear first. And they do so roughly tracing this graph here. This is a continuous version. This should really be a series of discrete points. And the small cycles appear much, much earlier, around a interval width of n to the minus 1.5, and moving up to approach the n to the minus 1 threshold that we see in the Erdős-Rényi random graph. And this is perhaps not surprising, because you would expect small structures to appear first before large structures, just kind of intuitively. This intuition is not borne out in the static random graph. It is in the temporal random graph. But it also maybe changes some of your intuition when it comes to money laundering, because the takeaway from this is that if you want to launder money quickly, i.e. within a short window, it is much less suspicious to do it via a small number of intermediaries and thus have a small cycle than it is to do it via a large number of intermediaries, at least in the doubly random temporal graph, because small time-respecting cycles are much more likely to show up quickly. So bear that in mind for anyone who wants to fiddle funds in the future. I probably can't say that. The other thing that we're interested in after temporal motifs are connectivity properties. And connectivity properties are probably the best studied aspect of random temporal graphs, especially when it comes to structural thresholds. And there has been a large body of work, especially on the random simple temporal graph, characterizing all sorts of behavior. So, for example, we have thresholds for point-to-point connectivity, all-to-all connectivity, temporal sources. We know things about the emergence of a giant connected component, and even how the lengths of time-respecting paths grow. But something that a lot of this work doesn't really consider is how well connected the temporal graph is once it's kind of passed these kind of binary thresholds. We would really have liked to have done this with either expansion or some kind of temporal analog of expansion. That's the kind of classic random graph theorist thing to do. But unfortunately, as far as we are aware, there isn't a really strong unified definition of temporal expansion. And so we have instead kind of opted to use this doubling time metric, which is a kind of imperfect analog for expansion in this setting. So the doubling time of a set of vertices is the minimum time step such that the vertices in the set can reach at least as many vertices outside of the set as there are vertices in the set, i.e. it's the amount of time it takes for the reachability ball centered on that set to double in volume. And then the doubling time of a graph, a temporal graph in general, is the maximum doubling time over all sets of vertices of size at most n over 2. And I won't leave you in the dark. We were able to obtain a relatively tight characterization of this for at least some doubly random temporal graphs. The kind of caveat here is that this only holds for continuous doubly random temporal graphs, and it only holds if we have a fixed number of labels per edge, i.e. our distribution has to be degenerate. But with these caveats, we're able to say that with high probability, the doubling time of a DRTG falls up to subconstant factors with high probability at 2 log n over xn, where x is the number of labels on each edge. And actually, even though we're not able to do this for Bernoulli random variables, Bernoulli label distributions, which is what typically we would use to simulate the random simple temporal graph, by using a trick where we essentially take a slice of the DRTG right at the start, we can actually simulate a random simple temporal graph well enough that we can obtain the following result. And we can show that there is a threshold in the density of a random simple temporal graph where below 2 log n over n density, with high probability, there exists at least one set of vertices that does not manage to double its reachability ball over the lifetime of the random simple temporal graph. Whereas if we are meaningfully above this threshold of 2 log n over n, we, with high probability, all sets of vertices are able to double the size of their reachability ball. And this is kind of interesting in that this corresponds to a known threshold of the random simple temporal graph. If I remember correctly, this is the same threshold that exists for the temporal sources or temporal sinks to exist. And this kind of falls in between all-to-all connectivity and point-to-point connectivity, which is kind of fun. In the name of time, given that this is the last talk and I don't want to keep people from the drinks reception, I will skip over the map of the analysis and move straight to the open problems and future work. So the big open problem for us, I think, with the DRTG itself is that all of our results are under the assumption that we have a uniform distribution for the timing of the labels, right? We allow this arbitrary label distribution for the number of labels, but we require the uniform distribution of the timing. And this should be relatively easy to change to an arbitrary timing distribution for the connectivity results and reachability results, because that's just going to kind of shift things around a little bit. But for the motifs, I think this represents a much more serious challenge because we do a bunch of order statistics under the hood, and order statistics for non-uniform random variables is very unpleasant. Then kind of zooming in on the motifs a little bit more, we had this strictness and simpleness condition for the motifs, and it'd be very nice to be able to make the statement that we made or something similar for all temporal motifs. I think strictness is quite easy to get rid of. I think simpleness is going to be quite challenging to get rid of, because there's a lot of kind of correlation under the, like, within the calculations, which you would have to handle much more carefully if your motifs are non-simple. And then finally, for motifs, I mentioned briefly earlier about the idea of growing motifs, and this mapped naturally to questions of, for example, the length of the longest time-respecting path, or the delta temporal clique problem. Both of these can be simulated by looking at the size of large temporal motifs, but both of these require very different approaches, and we actually took a look at the delta temporal motif problem, and we were unable to obtain really very sharp thresholds for it. And this is due to the fact that the label distribution and the ordering show up so strongly in this setting once you move away from constant size motifs. And then finally, for the reachability and connectivity results, these doubling time results, we had this degeneracy and discreteness conditions, like we only worked for the degenerate distribution and in the continuous DRTG, and it feels like both of these should be restrictions that we can lose. I think that the degeneracy is probably much easier to lose with a slightly more sophisticated probabilistic argument. The discreteness probably requires a slightly different approach, because in discrete temporal graphs, the nature of a time-respecting path matters much more. Like strictness and non-strictness appear, for example, where they don't really in the continuous version. And then finally, and perhaps the most vaguely, but also maybe the most importantly, we ended up using doubling times because we don't have a really good notion of temporal expansion, at least that we know of. And I think that this would be very, very useful for both the analysis of random temporal graphs, but also the design of randomized temporal algorithms. If anyone has any ideas in this direction or knows of any work in this direction, please let me know, either after the talk or offline, because I think this is a really important question. And in fact, I think if there are two takeaways that I would like from this people to take from this talk, it is firstly that temporal motifs are kind of interesting and they behave closely enough to subgraphs or static graphs that they are very powerful, but they also behave differently enough that they are interesting. And also that we really need a good notion of temporal expansion, and that this feels like a bit of an obstacle at the moment. But that concludes my talk. Thank you for listening, and if anyone has any questions, please ask them now or offline. Thank you.
Thank you very much. Are there any questions in the audience? There a question in the online? No.
There is a question from Arnaud.
Sorry, I will.
Yeah, should open.
Cannot see it with us.
Sorry about that. Yeah, I can read it out loud. Does the strictness of the motive imply that subgraph realizingist must be proper? I may have missed the motive.
No, it shouldn't do. The strictness of the motif only implies that when we're actually looking for the edge labels that make up the motif, they cannot appear. If there is an order between them, they cannot appear at the same time. We can have non-proper temporal graphs with non-strict, with strict motifs showing up inside them. It just which edges of that non-proper temporal graph can be used in the realization of the motif will be restricted as a consequence. Sorry, that was a little bit messy. I hope that explains what I was talking about. Yes, in this case, assuming that the two edges, that the adjacent edges, like the abutting edges, have an order over them. If we do not have any ordering over these edges because our ordering can be partial, then there is no restriction in play.